Vale. Ups. Minimizar. Voy a dejar así ya. No, my peers, they're tough stuff. Okay. Well, thank you very much for the invitation. It's a great pleasure to be here, and thank you very much for the nice introduction. Indeed, you can see that we are friends, so this was a very nice introduction. Okay, so I've been asked to give a talk about cosmic strings and the gravitational wave stochastic background that they produce. And I've been asked to be as much pedagogical as I could be, so I'll try. So I give a very extended introduction on cosmic strings. And then I'll talk at the end about the work I've been doing related to this subject with a bunch of collaborators from Tufts University, especially with Ken Allum, Ben Schleyer, Xavier Simmons, and Jeremy Wachter. Okay, let me see if this works. No, it doesn't. I don't know why. Oh yeah, good. Thank you. Okay, so the outline of my talk is this. So I'll give an introduction of cosmic strings, explaining what they are and what the dynamics. Then I'll talk about networks and what are the things that we need to know about these cosmological networks in order to give a good estimate or an accurate estimate of the stochastic background of gravitational waves. Then I'll discuss current and future gravitational waves observed, how we can put some constraints on this. And I conclude with some open issues that we need to discuss for the future. So let me just start by giving you an introduction to cosmic strings. So the first thing I should note is that cosmic strings appear in many models of physics beyond the standard model, meaning we are going to be describing models of the early universe, which go beyond the standard model, meaning at very high energies. And as such, if we can learn something about them, we are basically learning about physics at very high energies. Okay, so even though I'm going to be talking about gravitational waves, our final goal is to learn about particle physics, okay, at very high energies. So in some sense, I mean, people nowadays like to say that gravitational observatories are sort of high energy observatories as well, high energy particle physics observatories, because you can learn from high energy from there. And we will see how this can happen in this case. So when we think about physics beyond the standard model, we think about, as I said, very high energies, and we know that the universe, or we think that the universe has gone through several stages, several phase transitions. So depending on the phase transition, you can have different patterns of topological defects. You can get domain walls, you can get the strings, you can get monopoles. So today I want to talk about only one kind of defects, which are strings. So what is the most important characteristic of the theory that you have to have in order to have strings? Well, the thing to do is to look at the vacuum manifold. So the potential of AI in it has this shape, where the only minimum is this one. As the temperature of the universe decreases, the potential changes. Now the potential develops a expectation value for phi. So this, in this case, this would be the minimum, right? The vacuum manifold. So if the vacuum manifold, instead of being a point, as I represented here, is, for example, a circle, as I will describe in a second, then this vacuum manifold would have non-contractible loops. And this is the characteristic that is going to describe the formation of strings. Okay, so let me just give you an example. In mathematics, by the way, this is described by saying that the first homotopy group of the vacuum manifold is non-trivial. I can discuss this in more detail. It's just a mathematical way. Let me give you the simplest example where these strings appear. So the simplest example is a four-dimensional theory with a complex scalar field, phi, and with a potential that only depends on the expectation value of the modulus of the field, right? And for example, let's take for concreteness, let's take this type of potential, this Mexican hat potential, that has this shape. Now, there are two important things that I want you to remember from this potential. The first thing is that, as I said, it doesn't depend on the phase, right? It's invariant in this angle. It only depends on the modulus of the field. The second thing, it has a minimum, which is described by this circle here, which is where the value of phi, the absolute value of phi, is equal to eta. Okay? So here is the vacuum manifold is a circle, and therefore it has uncontractable loops, right? Because if I make a loop around the circle, I cannot contract it being inside of the vacuum manifold. Suppose as if you imagine that the vacuum manifold was a sphere instead of a circle, if I take a sphere, two-dimensional sphere, and now I make a loop, the loop on the sphere can be contracted to a point without ever leaving the sphere, right? If the vacuum manifold was a sphere, you would have contractible loops. Here, you have uncontractible loops, okay? Okay, so this is one of the things that I wanted to remember. So in fact, this is one of the things that I said before, this is going to be the characteristic to form strings. The other thing I wanted to remember is that the only parameter in this theory that has a scale, has units of energy is this scale eta, okay? And as you go to phi equals to 0, eta to the fourth describes the height of this potential, okay? So there's only one parameter in this Lagrangian that has units of energy, and this is eta. Okay, so how can we get the strings from this model? So let me just present here two different pictures. On the left is the field space with this potential. On the right is real space, okay? So it's a two-dimensional slice of a real universe. So as the symmetry breaking happens, the universe can decide to be in the blue phase, but it's as good as the red phase or is as good as the green phase, okay? So all these phases are equivalent. Now, what is more interesting is when we couple this to cosmology, because in cosmology, we know that there are horizons. Horizons means that they're distance, I mean, positions in space, which are so distant from one another that they don't have, or they haven't got enough time to talk to one another. Okay, they are not, or they haven't been in constant contact. So that means that we can imagine these 3 points being in different horizons at some point in the early universe. And because they haven't got enough time to talk to one another, they could have decided to fall into different colors, different phases, right? So as we know, the universe expands, so this horizon distance grows, and eventually all these points are going to collide at some point. Now, when they collide, they have to do something about what is the field going to be at the center. They cannot decide on one color because, I mean, who's going to win? So if you want to respect the boundary conditions at infinity of having these phases at infinity, and by continuity, the only way that you can do is to go to the top of the potential, right? So going to the top of the potential, you can see that you're going to have some ribbon in the center of this configuration that has some energy density, which is high, which is related to this eta to the 4th that I was talking about before, right? So in fact, this is basically the way a vortex is formed. It's a two-dimensional surface, right? So this is similar to vortices in superconductors or in superfluids. So we can extend this picture to 3 dimensions by saying, well, let's imagine the same thing happens in other directions. And then by continuity, what we see is that there's going to be a string here in all these centers where there's a high energy density stored in there. Okay, that energy density has to do with the height of the potential, which is basically the energy that the universe had before the phase transition happened. So this object is sort of a relic of a previous phase of the universe. Okay, so this theory that I presented is a very simple theory, but it has and describes, actually is a good description for global strings because it has a global U1 symmetry. But for the purposes of my talk, I want to talk about local strings instead of global ones. So I'm going to introduce one more ingredient in the theory, which apart from having this scalar field, I'm going to introduce a vector field, like a Maxwell type of vector field, except that because of the symmetry breaking process, the Higgs mechanism, the vector field is going to acquire mass in the same way as the scalar field phi. So in this theory, the vacuum manifold is still the same. Phi, when phi is equal to eta, this is the description of the vacuum manifold. But the difference between this and the previous one is that all the degrees of freedom in the vacuum are massive, while in the previous one, there was one that was massless. And this has important implications for strings, so I'm going to stick to this one. Okay, so I can have a situation with similar boundary conditions as the one that I presented earlier, a field phi, and when you go to infinity, the field, just basically the face of the field winds around the vacuum manifold, as the one that I presented earlier. And now there is something that the vector field also does, because if we want this object to have a finite energy, you realize that because of this covariant derivative, the vector field has to also acquire some expectation value. And in fact, if you work it out, what this ansatz means is that there's going to be some magnetic field stored in the center of this string. Okay, so in fact, these objects are nothing more than the relativistic version of the Abrikosov vortices of superconductors, right? As you know, in real superconductors, when you have a slab of a superconductor and you put it into a magnetic field, the magnetic field enters in the superconductor in tubes, right? In these vortices, okay? So that's the non-relativistic solution of the same equations that here are relativistic ones, okay? So we can solve this ansatz for this function f and this function alpha, and well, put in the equations of motion, you find this profile. As I said, in the vacuum, these two particles are massive, and their masses are related to eta, the only parameter that has energy, units of energy. The other characteristic is that these functions only differ from their value in the vacuum on a distance which has to do also with the inverse of eta, or basically the inverse of the masses. I'm assuming this, making a slight simplification here by assuming that both these masses are exactly the same. You can change that and you can complicate the model a little bit, but let me stick with that plan for simplicity. Okay, so the story is that most of the energy is concentrated in some small region that is basically concentrated in a distance which is of the inverse of eta, and eta is this scale of the symmetry breaking pattern. This scale of energy, the symmetry breaking pattern. Okay, so what are the properties of these strings? So the first thing to notice that is very important is these objects are stable. They are topologically stable. Why are they stable? Well, they correspond to the lowest energy configuration given the boundary conditions that the field winds at infinity. Okay, so given that boundary condition at infinity, there is no other configuration with lower energy. So therefore, how can they decay? Because they don't have anything to decay to. Okay, it's like if you ask, why is the electron stable? There's nothing else that has charge and that has low energy. Therefore, it cannot decay into anything, right? So this is similar to that. There's this topological charge that tells you that the topological charge cannot be violated, and therefore, if you have the lowest energy configuration with that topological charge, that has to be stable. Now, this has important implications because it means these strings cannot have ends, right? Either you have closed loops or you have infinite strings, or as infinite as you want, in the sense that if they go across the horizon, well, who knows? But they may eventually come back together, but they cannot ever have ends. Okay? All right, the other important ingredient here is that these objects are Lorentz invariant. What I mean by this is that the equation of a state is that the energy density is equal to minus the pressure, the other way around. Okay, so it's like an effective equation of a state is the one of a 1 + 1 dimensional Loyal constant. Okay, this is very important. This is actually very important because it's going to mean that these objects are very relativistic. Okay, and this, as I'll explain in a second, is very different from your normal strings, your shoelaces. Your shoelaces have a lot of mass but no tension. This is good because otherwise you cannot tie them up. So these are very different objects. Their tension is the same as the energy density, and it has important consequences. And finally, I'm assuming also that the only massless degree of freedom that they couple to is the gravity. And this is where changing the model was important, because the only degrees of freedom in the vacuum were massive. So there are no degrees of freedom coupled to the string which are massless, except the graviton. Which means that if you wiggle this string, it cannot radiate massless particles. The only particle that it can radiate is gravity. Okay, and gravitons. Now, these are my assumptions for the rest of the talk. Of course, you can violate any of these assumptions and make a model with different ideas, but the phenomenology and the results are going to change quite a bit. So let's just stick to this plan. We can discuss later on, if you want, what happens if you violate any of these things. Okay, so let's get a feeling for these strings. Let's put numbers, but numbers, real numbers, not like relativistic or normal. I mean, I want normal units. So what am I thinking of when I'm talking about this scale of eta? Well, as I said, it's physics beyond the standard model. Prototypical example is ground-unified theory, right? Which has so many scale associated of the order of 10 to the 16 GeV. Okay, so let's think about what happens for the strings of that kind. Since everything depends on that scale, I should be able to write everything in terms, all the properties in terms of that scale. So in particular, what about the thickness? The thickness, I said, is inversely proportional to eta. But if you put in normal units, it turns out that for 10 to 16 GeV, these strings have a thickness of 10 to minus 30 centimeters. Okay, these are particle physics tiny, right? It's tiny, tiny thickness. What about their energy per unit length, or their mass per unit length? Well, this is huge, 10 to 22 grams per centimeter. If you work it out and you multiply, if you imagine they have a string which is straight on the diameter of the Earth, it has a mass which is of the order, of a few percent the mass of the sun. Okay, so it's a tiny object, but it has a huge amount of energy per unit length. Okay, this is because we are talking about energies, which are very high energies in terms of everyday life. The tension is also huge. I don't know if there is a way to describe what this tension means, but somebody said that you could hold, I don't know, like a huge galaxy just at the surface of the Earth if you have a string pulling out. Okay, so it has a huge tension. Okay, so since I said there's only one parameter in this theory, and we want to study gravitational effects, let me describe for the rest of the talk the strings by this dimensionless parameter, which is g mu, where g is Newton's constant, mu is the energy per unit length of a string, which you can translate basically into the ratio between the symmetry breaking scale of the string eta and the Planck mass. So for 10 to the 16 GeV object, this thing is 10 to minus 6, right? It's roughly 10 to minus 6. And the important thing for you to remember is that for ground unified theory, this g mu is very small. That's the only thing I want you to remember. And if you have, of course, from the ground unified theory all the way to TeV, for example, if you want to say that this is the lower bound for beyond the standard model of physics, this number becomes also very, very small, even much smaller. Okay? Any questions so far? No? Okay, so let's continue. All right, so we said that there are models in particle physics where you can find these objects, you can find the exact, the numeric, if you want, solution of these profiles. So they exist as in part of the spectrum of the theory. But the most interesting question is, do they get formed in the early universe, in our real universe? Well, this idea goes back to Keeble in 1976. He said, well, if there are these phase transitions, there is a lower bound on the number of these objects that you will form just by causality, okay? You cannot say, well, the number is so small that I'm not going to see any of them, because by causality, you can say there's a lower bound of these objects. Of course, assuming that, of course, the theory has these properties that I described before. And also the other thing that is sort of an assumption here is that if inflation is in the picture, inflation happened before the phase transition that forms the strings, right? Because if you first form the strings and then you have inflation, everything gets diluted so much that you would not see any string. In fact, this was the idea of inflation, to get rid of monopoles, right? So you do the same thing with the strings, everything would be disappearing, we would not see any strings. But this is not a very strong assumption in the sense that, in fact, we know that inflation has to end. So one way in which inflation can end is by a phase transition. And it may be that particular phase transition that produces the strings. So it's not so unreasonable to think that this happens after inflation. And in fact, there are models of string theory that also produce this, and also models where you produce cosmic superstrings at the cosmological scale. So this may be a little bit shocking to some of you, but this is a different way to think about cosmic superstrings. Cosmic superstrings, sorry, superstrings. The superstrings of a string theory, we used to think about them as if they were tiny objects with mass, and therefore, from very far away, we look at these things as particles. This is right. But if you couple this idea to the idea of inflation, for example, you can imagine that a tiny string that is sort of vibrating at a very small scale could be stretched to a cosmological size by the expansion, very violent expansion of the universe, right? If that happens, then the string that was a quantum object becomes a very classical object, right? Because you're sort of pumping so much energy into it by stretching it that it becomes a classical object. Once it's large, cosmologically large, and classically behaves like a normal cosmic string that I will describe today. So one way to observe also cosmic superstrings would be by looking at gravitational waves in the same way that I described today. Okay. So these things get formed. We can simulate this process of formation by taking a lattice in the 3 dimensions and throwing random faces on the links, on the vertices of the lattice, and then identifying the places where the plaquettes have some winding as a string going through this plaquette. So we can follow that position of the string, and the picture that emerges is this one. This was suggested by Tamay Vatsespati and Vilenki in 1984. This is a modern realization of the same thing. So here you see that so strings have different colors. The blue string is the one single string that goes many, many times across the box. This box has a periodic boundary condition. So the one that that comes out this way enters that way. So what you see in this picture is that clearly that string dominates all the energy of the network initially. And in fact, this 80% of the energy here is in that one single infinite string, if you want. I'm calling it infinite because it goes many times across the box, so many times across the horizon size at that time. But then there are other loops which are also formed. This is around 20%. So this is the initial conditions. What we want to see is how do these things evolve? So for that, we need to know what kind of dynamics do strings have. So let me just take a step back and think about a simpler thing that we know, which is a particle, a relativistic particle. So what's the action for a relativistic particle? Well, it's just the length. Well, this should be multiplied by the mass. This is just the length of the world line, right? And it should be proportional to the mass. The way in which we know that it should be the world line is because it's one of the things that describes the trajectory is Lorentz invariant. The thing that is, how do we know this proportional to the mass? Well, if you take the non-relativistic limit of this action, you go back to the Newtonian physics. So that fixes this coefficient to be the mass, okay? So this is the relativistic particle without any structure inside, just like a point. So what we want to do is to generalize this to a string, okay? Now in principle, you may say, well, this is different in the case of string because in string has any density and has tension. So I have two parameters, not just one. But remember that in this case, the relativistic version that we just described, the any density is the same as the pressure. The equation of state was that these two things are the same. So there's only one parameter. Okay? So the action that is the obvious generalization of the particle one is this one, which is the non-Bogota action, that is proportional to the only parameter, which is equal to the any density or the tension, the same. And then what we are putting here is not the length of the world line, is the area of the world sheet, because as the string propagates in space-time, it describes this world sheet, this membrane, right, that is described here. Okay, so this is the area of the world sheet. So of course, what we want to know is what is the position of the string in the space-time, and we want to parameterize this world sheet in terms of two parameters. One, there is a space-like parameter sigma, and another one, there is a time-like parameter, which is tau. The interesting thing about this is in the same way as in the world line, it was invariant, the reparameterizations of our parameter tau. Here you can parameterize this world sheet in the way you want, right? The physics of the evolution of the string should not depend on how you slice or sort of make a grid in this world sheet. So this is going to be important in a minute. So we can calculate the induced metric, which is the one over here, and the calculation of the area, and these are our sort of observables. Okay, so we can calculate the equations of motion from there. And as I said, there is a huge gauge invariance here because there are many different gauges that I can take, many different coordinate systems that I can take in this world sheet, and the physics should be invariant under those. So I can pick the ones I prefer, and then find the equations of motion in that gauge, like we do in electromagnetism, right? Or in gravity, right? So let me pick a gauge which is described by these two conditions, which they have a physical meaning. The second one says that x dot, which is the velocity, is always perpendicular to the tangent vector of the string. That makes sense because if the string doesn't have any structure, if you have a straight string, there is no meaning of a motion of the string along the string itself, right, along the tangent vector, because it's invariant. You could not see if it is. There's no way to tell if it is moving or not along this direction, right? The only meaning velocity is the one that's perpendicular to it. So that's the second condition. The first condition tells us that sigma, which is described here by x prime, is a parameter that describes the energy per unit length on the string. Okay, this is the way in which sigma is parameterized in the string. So why do we pick these conditions? Well, we do this because the equations of motion that come out of this action become extremely simple. It's just the wave equation. It's just the wave equation for x. And we know how to solve this equation is within our capabilities. And it's basically a solution that describes waves propagating both ways. Well, what the string theory is called right movers and left movers, right? So waves propagating in one direction, waves propagating in the other. So there's two vectors, A and B, are in some sense arbitrary, except that this whole thing has to respect these gauge conditions, right? So you have to put this back in here and make sure that these two functions satisfy these two gauge conditions. And the only condition is that the derivative of these vector functions with respect to its argument is normalized to 1, okay? So these two functions, A and B, or A prime and B prime, live on a sphere of a unit sphere, okay? So this is very simple, right? It tells you that you can go home today and write many solutions and play with them if you want. The only thing that you have to do is to draw a line on a two-sphere unit vector, two of these functions, integrate them, and just plug them here, and you have the solution for the evolution of the string at all times. Okay. Okay, but before that, let me just go back to the non-relativistic case. So as I said, in the non-relativistic case, we have two parameters, mu so the energy per unit length, or the mass per unit length, and the tension. And we know from our high school physics how to look at the waves propagated in this string. And we know that the coefficient that is in here on the wave equation is exactly related to the velocity of the propagation of the waves. So we already see something here, because in our case, these two things are the same. It seems to suggest that V is to be 1. 1 in these units means the speed of light. So indeed, already thinking in the non-relativistic case, we could already guess that when one of these functions is on a straight string, it's just going to be moving at the speed of light, right? In fact, this is what happens. You take a wave of left movers against the wave of right movers, and well, you just write the equation for all times, and you see the move at the speed of light, and until they collide, and they just pass through one another without much of an interaction. There's an interaction in the sense of delay in the interaction, but at the level of this equation, you don't see that. Okay, so this is assuming that the theory or the string moves exactly like Nambu-Goto. So you may ask, okay, but what about the original theory, the one that had to do with the field theory? Do they move exactly like this? So people studied this in the past, and for example, did a simulation like this, which is a lattice field theory simulation. These are now real, so you're simulating a bunch of points on a lattice, right? So you see that the collision of these strings, of these wiggles, is exactly following the Nambu-Goto one, the one that I described before, except in regions where the string curves itself so much that it curves at the level of the thickness of the string. When the string curves at that level, the Nambu-Goto action breaks down, and there is a possibility of radiation. But you see, there's only radiation there. There's no radiation here, no radiation there. There is no other radiation in the evolution. So the strings behave like Nambu-Goto, except in regions of high curvature. Okay, high curvature means curvature at the level of the thickness of the string. Yes. Right. Very good question. So this is radiation is just in terms of the particles that propagate in the vacuum of the theory, which are this massive scalar field, massive vector field, both of them. Yeah. So that's the other way of thinking about this. If you wiggle the string, since it's coupled to these massive objects, the only way you can radiate it is if you wiggle the string with the frequency, which is of the order of the mass of the particles that can propagate in the vacuum. So as long as you don't have frequencies or curvatures of that order, if the string is smooth enough, then you would not have any radiation, and therefore Nambu-Goto would be a perfect description of the theory. Okay, but as I said, it has been checked doing the full field theory. Okay, so the only other thing, the only other thing left that we have to study is what happens when there are interactions between the strings. And what happens is exactly this, that I was too fast. So when these two strings come together, what happens is that strings intercommute and they exchange partners. So this guy is going to go with this one, and this one is going to go with that one. Okay. Here you go. Now, why is this important? Well, this is very important because it means that the strings can create loops. An infinite string can sort of curve back on itself, like this one, and create a loop. So it's not, the loops are not the ones in the initial conditions. Many loops are going to be formed during the evolution of the strings, many more than the initial conditions. The other important thing that you see is that there are discontinuities in the tangent vector due to this process that get created. So this can accumulate on long strings, and as we will see later, this could have important consequences for us. Okay, what about these loops? How do these loops evolve? Well, just to gather some intuition of what kind of evolutions we have for loops, let's think about the simplest possible loop that we can think of, which is a loop that starts being a circle. Okay, it's actually always going to be a circle. So I'm going to parameterize the position of the string by this 4 vector. And so for a constant time, I parameterize by sigma the position along the string. Okay, so if you take at each moment in time, this is just a circle of radius r of t, right? So with this parameterization, I can plug it into the number go to action that I had before, and you get this effective action for the only free parameter, which is the radius of this circle. You can find the equations of motion for this, and this first integral of the equations of motion, which you can integrate. Okay, and this is an interesting solution because it tells you that if you start with t equals to 0 at rest with some radius r naught, as you evolve in time, this radius is going to decrease, right, all the way to 0. Now, this 0 is going to happen when this thing is what? Pi over 2 times r naught. So at that time, this cosine is 0. But actually, the most important thing I want you to remember is that when this is 0, its velocity, which is the sine instead of the cosine, is going to be 1, right? So this thing is going to collapse due to the fact that this thing has tension, right? It has tension. It's like a rubber band. So it wants to minimize the size. It wants to collapse. But the fact that this thing has relativistic properties says that at the end, the velocities that you're going to have, the typical velocities you're going to have, are relativistic. And in fact, by the time it collapses completely, each point is moving at the speed of light. Okay, so I don't know, in case it's not clear by the solution, that's the solution. So starts with some size, collapses to a point, and in fact, if you want to continue it, it comes back up, right? So one way to think about this is that initially, when it's at rest, all the energy is in potential energy, in the fact that you have a length, and this length, it wants to shrink, but as it shrinks, the length is smaller, but the velocity is larger. So energy is conserved because you transform kinetic potential energy into kinetic energy, right? As it crosses the point, it goes at the speed of light, and then it goes back up. As it goes back up, it slows down, increasing its size and decreasing its velocity, right? So bottom line, these things are periodic. First thing that you notice, they're periodic, right? They oscillate forever, and they have velocities which are the speed of light. Not surprisingly, because it's a very relativistic object. They cross. But I mean, in reality, I mean, this is in the number what they would cross. But in reality, in the field theory, if you were to do this, and people have actually have simulated this in field theory, of course, what happens is that by the time the thing collapses so much that all the energy is concentrated in a region, this could just break up into particles. Okay, so if you take a perfect circular a string, it will not do this in field theory. It would just explode in particles because the topological stability disappears, right? Because if you cut on a plane like this, here you may say this is a winding of 1, but this is a winding of -1. So when they collide, they can annihilate. Like if you have a vortex and anti-vortex in 2 dimensions, they can annihilate to nothing. You can leave this in terms of particles. Or actually, some other people have simulated this, including gravity. And there's another process which can happen, which is that if the loop is large enough, then you concentrate so much energy in some point that you can create a black hole. So this is also interesting. All right, so this was a very special example because I make it perfectly symmetric, perfectly circular. It's just to give some intuition of what these things do. But in fact, we have the general solution, okay? You can find any loop you want. You just put functions A and B, whoever you want. The only thing that you have to do is to make it into a closed loop. Once you make it in a closed loop, you realize that the loop is going to be periodic. It's going to oscillate whatever it is doing, but in a periodic way, okay? Actually, the periodicity is proportional to the length, as we saw in the previous case. Now, they oscillate because they have their tension, and they are typically relativistically. So you can see where I'm going with this, right? I gave you already very interesting information. First thing, I said, the mass of these objects, the strings, the straight string is huge, 10 to the 22 grams per centimeter. Second, they have tension, so they oscillate. Third, the velocities are very large. So these are perfect instruments for gravitational waves, right? You have a huge amount of mass and it's oscillating like crazy. I mean, what else is better than this? We produce gravitational waves. Okay. Actually, there is also an interesting point which is called a cusp, which is a point where the function b prime is equal to minus a prime. You can compute the velocity. You see if these two functions are the same at that point, and its modulus of each one is 1, this becomes 2 divided by 2 becomes 1, which is the speed of light. Okay, so these points are points where these two functions b prime and minus a prime cross at some point. And you can color the string position, like the one here, with the velocity. And you can see that there's a point there where the string moves in a transverse direction at the speed of light. Okay, so this is also an interesting event in the evolution of the string. And it's actually quite generic in the sense that, if you have two functions on a sphere, it's very easy that these two functions are going to cross, right? You would have to arrange it in such a way for them not to cross. For example, this particular loop, which is a burden loop, the one at the bottom, at the top, it's an analytic solution you can find, and you see that there are points like this that are exactly like the one here, right? Let me do it again. Oops, not that one. This one. So there's one here, one, and one there, two. There are two events, these two cusps in the evolution of a simple loop that you can write down, okay? In fact, this type of event is going to be pretty generic for strings. Okay, so why are loops important? Loops are very important for the whole story, apart from the fact that that this is exactly the signal that we are going to want to compute and observe. They are very important to make the whole model viable. Why? Because if you didn't have loops, the energy stored in the network of strings would increase as a function of time. And at some point, it would become the dominant any density in the universe. This is a disaster from the point of view of cosmology, right? We want this to be a network of strings which is subleading. We know how the universe evolved in the radiation era. It was dominated by radiation, not by strings. In the matter era. So we want some other fluid, the strings, which are subdominant during this time. So what's the way in which you can make a subdominant? Well, you have to release enough energy from the network into radiation. And this is done because the network produces loops by self-intercommutation of the long strings, right? Once the loops are produced, they start oscillating. When they oscillate, they emit gravitational waves, which is radiation. So the whole network loses energy, emitting all its energy into gravitational waves. Of course, this is the reason why we wanted for the strings to be viable, but this is also actually our signal as well. This is what we are interested in to calculate. So the important thing is that by the production of these loops, there's no monopole problem. There's no problem in which the network is dominated, the density of the universe is dominated by this network. Okay, so let me just start now the calculation of the gravitational waves. So let me first start with the back of the envelope calculation, where we calculate what is the rate of any loss or mass loss of an object like a loop. So we can use the quadruple approximation, and the result is that when you do sort of very unwavering arguments, the result is that it's just proportional to g mu square times this coefficient gamma, and this gamma is a number that depends on the shape of the loop. It is of the order of 50 to 100. Okay? So that means that if this is m dot, is the rate of mass change, you can calculate or compute the mass as a function of time is the mass initially, or some other time t prime. And then this mass is decreasing with time linearly, right? Because this is a constant. And if instead of the mass, I put the length, remember that the length is basically the mass per unit length times the length, I can say that the length of the loop is shrinking on a rate which is proportional to gamma g mu, okay? So remember the g mu was very small, so gamma g mu is still going to be very small. So that means that this loop is going to be around for many, many oscillations, right? It's going to be oscillating and emitting gravitational waves for many Hubble times. So this is good. This is exactly what we want. We want this loop to produce all these gravitational waves that get to us, because gravitational waves do not get absorbed by anything. And we want to collect all this information today, right? So this type of stochastic background of the whole network of loops producing gravitational waves has been calculated before many times. Let me just sketch what is the way that you can calculate this. So remember, what we want to do is to calculate the contribution of the whole network and the whole history of the network to the gravitational waves today, right? So let's fix the frequency at which we observe these gravitational waves. And in the way that people computed, the way people want to represent this is by this omega, which is the fraction of any density in the universe in terms of gravitational waves. So at some particular frequency today, in order to do that, we have to do a double integral. Why a double integral? First, the integral in time is obvious. We want to integrate across all the cosmological times until today, because we want to see the contribution for all this network throughout the time, right? The other integral comes from the fact that if you fix the frequency today, and you ask, okay, at some particular time, what is the sources, or what are the sources that produce in this frequency? Well, at that particular time, you have loops of many different sizes. All these sizes contribute at a particular frequency today, because the loops have different shapes, and some of these wiggles on the string would produce gravitational waves of the frequency that is the one that we're interested in. That's why you have to integrate both these things. So in order to do this integral, obviously we need the number of loops. This is number of sources is important, of course. It must be proportional to that. Now, what is a little bit more interesting is that this is not only the density of loops, but it's the density of loops at any moment in time. So this is quite a complicated task, because you need to know this number everywhere. I mean, all the time, at any moment in time. And then we also need to know the power spectrum of each individual loop, or at least the average power spectrum for loops. So these two things are things that we can obtain directly from simulations. Okay, and this is part of the work that I've been involved in. So the first one, as I said, it looks a little bit complicated, at least to say the least, because even if you do simulations, this is for all times, from now till very deep in the radiation era. But how can I do a simulation for such a huge range of times? This is impossible. Well, this is where we caught a break, because the network of strings have this thing that is called scaling, which is some sort of steady state behavior or attractor behavior. So there are different ways to characterize this scaling solution. One way to say is that the energy density in these strings compared to the energy density in the universe becomes a constant, so it becomes a attractor. Okay, so it doesn't dominate or get diminished, it's constant. But the most important way to say it is that all statistical properties that have to do with distance scale with the horizon distance. So one way to visually say this is to say, imagine that you take a snapshot of the network at some particular time, and you take another snapshot when the network is double its size. Okay. Then take the original one and stretch it to be double its size, and compare that one that you produce by real evolution to the one that you produce by stretching. Well, statistically, you cannot tell them apart. Okay, this is what scaling means visually. So why is this very important? Because it tells us that if we reach a scaling, we know how to propagate everything or to estimate everything at any moment in time by this scaling property, by just scaling everything with the horizon. So we don't need to do an evolution from the very deep in the radiation hierarchy today. We just need to do it enough to find these scaling properties. Once we find the scaling properties, we can just scale them up and down. Okay. So this is why we do the simulation like this. We put the initial conditions that I showed you before, and you put in the expanding universe and evolve the strings with the non-Boovato equation of motion, and you get this this nice movie. You see that the density of long strings decreases because the universe is expanding. And from time to time, you see these loops being formed. Eventually, I remove them. And the reason why I remove them is because, well, they are oscillating, right? They are periodic solutions. So at some point, there is no point of keep simulating because we know exactly how they are going to behave. So we evolve long enough to find that the network is actually in a scaling solution, and then we take the properties from there. Yes. The density decreases because of expansion. If there is another phase transition, well, then we have to change this dynamics. But we assume that there's only one, and everything it's a relic from there. Okay. Right. It's proportional to the total density of the universe. Yes. No, this is only for radiation matter. Right. In this case, it would be diluted in the cosmological. Okay, so this is a simulation for to get this scaling solution. And in fact, if you look at the properties of these long strings, they have been scaling. But we're actually interested in the scaling solution also for loops. Remember that our signal is the loops oscillating and producing gravitational waves. So we need to know that these loops are also scaling. For that, in fact, we have to do a much bigger simulation, not 1 order of magnitude bigger than that, but 2 orders of magnitude bigger than that. This is what took a lot of time to do. Okay, but we did it, and we finally got this expression. For example, for the radiation era, what is the energy density of loops at all times? Remember, this is the number density of loops as a function of time, as a function of the length. And here is time and length. Okay, so we have one of the results from our simulation. We need to do the other one. Okay, so what is the power spectrum of gravitational waves for each loop? Well, the first thing to note is that there are discrete frequencies that each loop emits to, because the loop is a periodic solution, right? So the total gamma, the total power emitted, is just the sum of the power emitted at each of these discrete modes. This is important because, as I said, the length depends on this particular gamma, or this total gamma. But if we want to compute the power at each mode, This depends a lot on the shape of the object. For example, if you have a cusp, which we already introduced, the way in which the radiation declines with this number of modes is very slow. It goes like n to minus 4/3. We have kinks, which is also something that we talked about. It declines a little bit different. So it matters if the loops are dominated by cusps or kinks, how the power is going to change, right? So luckily for us, we have the loops. We have done the simulation. We have thousands of loops. We can extract them and look at them. And this is one of them that I can make a movie for. So you see a lot of things here in this movie. First thing is that if you notice a little bit, they are periodic solutions. So if you notice, they will come back to the same situation. The next thing you see is that there's not self-intersecting. This is very important. The loops that we are interested in are not self-intersecting loops, which are rare, not the typical ones. The third one that you see is the color. There are different colors there because I color the position of the string by its velocity. So you see that there are many different sections of this string. This is because this string has been produced after many strings before its formation were cut off, right? So in some sense, this string is the daughter of many generations of strings that have been chopped off. Okay? And this is how you can get one non-self-intersecting loop. I told you before that you can get the loop this afternoon mathematically if you want and make it oscillate. What I didn't tell you is if this loop was going to be non-self-intersecting. For that, you have to work a little bit harder. But the network works for us in that respect because it does many of these loops and eventually finds ones that are non-self-intersecting. Then we extract them and we put it in some file to evaluate the power spectrum. Okay, so we could do this directly from the simulation, but there's a problem with this because as the loop is evolving, it's emitting radiation, it's going to change its shape, and therefore the power of the radiation is not the same as the one that comes out of the simulation. So in order to take into account this back reaction, we basically took the loop as it came from the simulation and we smooth the loop at the smaller scales. Okay? Then we smooth it a little bit more at the larger scales or even larger scales. So these are the same loop at different stages in its evolution, right? And we can now compute the power spectrum at each moment in time. So this is a toy model, of course, for back reaction, not the real thing, but it gets smoother as the time passes. So we can do a histogram of the values of gamma, the gamma that is the total power of the loops. And you see that, for the last stages of this smoothing procedure, most of the loops are the constant value gamma of 50. Okay, so this value of 50 was pretty correct. The other thing that you see is that at the final stages, the loop looks very smooth. Okay, and it has these points there that really look very, oops. Let's see, there. There's a point there, which is very pointy and is very red. That describes a cusp. So we didn't put cusps in. The evolution, the smoothing, create these cusps for us, right? So that means that the power spectrum is going to have to be, in some sense, reflecting this fact that these loops are producing cusps. Let me just skip a few things here. So this is the final result of the power spectrum. The power spectrum as a function of n, the number mode, okay, and is multiplied by n to the 4/3 to represent the fact that this is not zero. So this is representing the fact that at very large n, at very high frequencies, these modes, these loops, its power is dominated by the cusps. Okay. Okay. So apart from the details, the important message is that okay, we've done both. We've done our homework. We have both these functions n and p, so we can do this integral. Okay, this integral is not difficult to do, and this is it. This is the way people like to present this, which, as I said, is this omega, or the fraction of energy in gravitational waves as a function of frequency. And I represented here different colors on different values of g mu. Remember, g mu is the scale of the string. So higher the tension, higher the amplitude of this gravitational wave spectrum. So there are a few interesting things here. One of them that should shock you is that the frequency range here goes from 10 to minus 10 hertz to 10 to 10 hertz. So we have a signal of a huge span in frequencies. Why is that? Well, it's obvious. It's because loops at the early universe were very small, so the frequencies were very high. This would be here. Later on today, loops are the size of the horizon, so their oscillating time is much, much larger, so their frequencies are much smaller. So the universe has changed over its evolution for a big factor, and this is reflected here, right? So there are two contributions for this. One is during the radiation era, which is a pretty flat distribution here, and then it drops down, sorry. And then there is another contribution that rises, which is the one from loops that are emitting during the matter era. Okay, the important thing here is that there is a signal in all the bands of all the observatories, right? There is a signal in the pulsar timing band at very low frequencies, nanohertz frequencies. There is a band. There's a signal in the band of LISA, for example, the space interferometers, and there is also an observation. A signal in the interferometers on Earth, for example, LIGO, right? So this is great. We have signal in all our current and future observatories, right? Not only that, because if we observe one, we can predict what the other guys are going to be able to see. Okay, so there's not too much room for saying, oh, okay, this thing is observed here, but then it's going to decline, because you have to change the whole picture to do this. So I think I'm running out of time, right? Okay. Okay, so let me just, because I think this is interesting. So the first thing, or actually the most important constraint at the moment from cosmic streams comes from pulsar timing. If you haven't heard, pulsar timing is a way to observe gravitational waves of the frequency, very low frequencies, the nanohertz frequency, by looking at the time of arrival of these pulses and see deviations from this time of arrival. And in fact, you can put limits on values of Gmu. Already a few years ago, we put some limits for the different observatories that were putting limits, upper limits in gravitational waves, right? So from that, you would say, well, Gmu cannot be more than 10 to minus 11, roughly in all the different observatories is the same. So note that this is 10 to minus 11. It's quite smaller than 10 to minus 6. So this is telling you already that this rules out any cosmic streams produced in the gravity theory, okay? Which is something that that is important. Also, it is important to know these streams are not going to be seen in the CMB, okay? Because the tension is so low that you will not see these deviations from in temperature fluctuations. This is much more strong. It's like 5 orders of magnitude stronger than the CMB bound. Now, more recently, a couple of years ago, Nanograph produced this 12.5-year data, and they report an observation of a common red spectrum on their observations. They haven't claimed detection yet because they didn't have strong evidence for this quadruple correlations, which is the sort of the signature of gravitational waves. But taking this value, you can say, okay, what are the constraints that I can put on cosmic streams? So they actually give this data in terms of contour plots in this parameter space of the amplitude and the spectral tilt of this characteristic strain, which is slightly different from the one I've been presented, but you can transform it into the quantity that I was talking about. So you can immediately put bounds on both of these things, the amplitude and gamma. And we did this 2 years ago. So you can constrain the value of G mu to be of the order of 10 to minus 10, almost 10 to minus 11, depending if you take the 1 sigma or 2 sigma range, okay? Now, the big uncertainty here comes from, well, it's not that big, but the uncertainty comes from the fact that we don't know this power spectrum P of n, which is how much power you emit at each mode. We don't know it with huge precision, right? Because we did this toy model where we smooth things out by hand, right? And in reality, you would have to do this better, which is actually something that we are working on now. So here what we did is, well, we put some different power spectra to see what the ranges of values we would get. And as you see, the results for the bounds on G mu are not that different. So roughly we get again 10 to minus 11, 10 to minus 10. But the interesting thing, as I said, is not that pulsar timing is the only game in town, because we have future observatories like LISA, the Big Bang Observatory, or Einstein Telescope, which should be somewhere over here, which is going to tell us much more. If indeed we are observing something at the pulsar timing band, we should observe by far a lot in LISA. In fact, if you say, let's take the bound from pulsar timing and let's compare with the sensitivity curve for LISA, and then you see a huge signal, right? This is the sensitivity curve. So there are 10 to minus 30, and here you have 10 to minus 10. So it's a huge, huge signal. LISA should be able to see it like right away. Okay. As I said, there are important things for back reaction, which I didn't have time to describe, so let me go to the end. So as I tried to explain at the beginning, cosmic strings are predicted in many models of this beyond the standard model, many extensions of the standard model. We have done these numerical simulations over the years, and we are entering a period where we say this is a persistent cosmology for cosmic strings, meaning that we have some certainty in the calculation of the number density of loops. And the only thing that is left to do is to do a precise calculation of the power spectrum. We have some ideas of what it should be, but we don't have a precise calculation. And this is something that, as I said, we're working on. Pulsar timing observations, current ones, put up already some very important constraints on the spatial parameters of cosmic strings. In fact, as I said, is the strongest bound of any observational signatures for strings. But in the positive side, if we can observe actually some stochastic background in the future, either we can observe that this comes from cosmic strings, or we can put some bounds on the scale of the strings. And LISA and Einstein Telescope has a huge range of possibilities that they should be able to see if they exist. So if LISA, for example, doesn't see anything in cosmic strings, the scale of the symmetry breaking gets so much low that it becomes a little bit sort of uninteresting in the sense that, I mean, it's still interesting, but it's not even related to the groundify theory. It's much, much lower. So even the current observations or lack of observations of gravitational waves puts very important constraints in the model building of the early universe, because, as I said, the current observations from pulsar timing already say that groundify theories cannot have a phase transition that produce local strings. Okay, period. They would have been seen already by pulsar timing. Okay, and I think this is interesting because it opens up a way to discriminate between many models of beyond the standard model physics in the early universe. Okay, thank you. Right. Right. So if you take a model of a groundify theory, this is of the order of G mu would be order 10 to minus 6, right? Okay. This line over here, okay, is the one for G mu 10 to minus 9. 10 to minus 6 would be over here, okay? But pulsar timing observation already says that this is ruled out. of course, if this were, I mean, if G mu was 10 to minus 6, LIGO would have seen it. But because, first of all, they haven't seen anything, but apart from that, pulsar timer says that the limit is 10 to minus 9, LIGO is probably not going to see anything. So from the fact that you don't see any strings with G mu 10 to minus 6, it says that if you want to work a model in the early universe, a granified theory that has a phase censorship that produces strings, this is impossible, because these strings would have evolved producing gravitational waves that we would have observed in pulsar timing. Okay, so okay, you can work at a model of granified theory. This is not ruling out completely these models, but somehow you have to avoid forming strings. Okay, it's not impossible to form strings. It's not necessary to form strings, but you know, you have to argue against this. Yes. Yeah, you can think it's a scalar field. It doesn't. No, it doesn't. In fact, it cannot be the Higgs itself, but it's a Higgs-like field, like you know, another field that is a much higher scale. But it's a scalar field like the Higgs. In fact, the potential looks like the Higgs. It was inspired by the idea of the Higgs at that time. Nowadays, we think, okay, there is some unification at very high energies, and is described by this scalar field that breaks the symmetry. Yes. Mm-hmm. Exactly. So right. Let me just go back to one. Okay, here. So you were saying as this thing evolves, it emits radiation, so it's going to change. Yes. So its length is changing linearly by this quantity. Yeah. So no, no. It will change its frequency because the length changes. So imagine that you start with the one that's a circle, right? How this would work? Well, it's apart from the fact that if it is a circle, more complicated gravitational wave, but let's imagine that you have some sort of gravitational waves. It oscillates, but then it changes, but changes is total extension, if you want. This is still oscillating relativistically. There is no damping. Yeah, the equation of state stays until the length, the radius of this loop is comparable to the thickness. So, which for us is much, I mean, it's a lot, much later in the game, right? If you imagine that the initial length is like, I don't know, a parsec, let's say, or whatever, you have a long wave from a parsec to 10 to the minus 30 centimeters, right? So this thing is going to oscillate, losing all this energy, and eventually when it becomes very, very small, it can explode, as I was describing before, right? And then you release all this energy, not in gravitational waves, but in particles. And then it goes to the second part of your question. That energy can, if you inject energy, you know that if you inject energy at some point, you may see it in the CMB, not necessarily directly in the perturbations in the CMB, but for example for these spectrum distortions, right? But you have to, I mean, this is actually quite powerful mechanism to see this injection energy. It's quite sensitive to this injection energy. But if I remember correctly, I'm saying this from memory, so I'm not sure. But the amount of energy here is in the usual mechanism where most of the energy is radiated in terms of gravitational waves, and only the last part is emitted in particles. This is so small for the values of G mu that I was talking about that probably you don't see it in this IC or whatever it is, this experiments. But yes, this is a good idea in the sense that it's something worth exploring. We keep this or?